Hello! So today I've decided to make life much more difficult for myself. So I've been working on a C++ library for one of my projects, and I have been thinking about using C as well. And I've seen a lot of comparisons online that show C versus C++, but they all sort of are abstract descriptions of what the difference is, and I want to have a hands-on and concrete idea of what the differences are between these languages. So I'm going to be making exactly the same language I made in C++. I should have said library that I made in C++ and am making in C++ in the language C as well. And this is going to be able to give me a direct comparison between the two languages. So today I'm going to start off by making a linked list in C. So we're going to go ahead and create a new directory, and we're going to call it data structures. Now in my C++ library, I started off by building a web server and only started making the data structures once I needed them. But knowing that I'm going to need them, I feel like this is a relatively easy way to start. Also, I'd like to mention that I have descriptions of what a linked list is and how the different operations work in my C++ library version, so I'll put a link to that in the video and you can see those if you want a more theoretical approach to the linked list. Today I'm just going to be building it. So this is going to start off with our node. And so I'm going to create a C file called node. And this is going to present a few challenges because some of the things I was taking for granted in C++, like overloading functions and class templates, are not available in C. So I'm going to be having to work around that just so I can see all of the things that C++ is doing for me when I actually make these classes and objects. Also, I want to point out that I am approaching this from an object-oriented background. I'm very familiar with using objects, and so my approach to C may have some sort of object-oriented flavor to it, which I'm sure will frustrate those who are already familiar with C. So look forward to that. So I'm going to be trying to make things that work relatively the same way as they do in my C++ library, and we'll just see how it goes. So I'm going to create my node, and here the node cannot be a class, it has to be a struct. So this is going to be fairly simple. So I'll just say struct, and we'll go ahead and use that. I'm going to call it node. But here is where I used a class template in C++. In C, I'm going to have to define a different struct for every kind of node that I would want to have a linked list for. So this is going to be a node of type int. And for now, I'm only going to work with ints. And as I need linked lists that use floats or character arrays, I will just make the parts that I need for those. So I'm only going to make things as I need them here. So this is going to have int data and a pointer to the next node in object. So I'll say struct node int pointer next. And that is all I really need for this node object for now. Like I said, in the future, I'll probably be adding things to this, but for now we are good to go. And so I'm just going to go ahead and create the linked list file as well. So let's call this linked list. And here's where you're really going to see my object-oriented approach to this. So let's go ahead and get rid of that. Because I want this linked list to itself be a struct. And I know that in C, member functions in classes, or structs in this case, don't actually exist. So I'm going to do it in a slightly different way. I know that this isn't the preferred way, but the way that you will actually implement this in the future makes it make a little more sense to me. So bear with me, you'll see what I mean in a moment. So I'm going to define my struct for a linked list of type int. And the linked list will, as always, have its head. So we need to include the nodes. And we're going to have a node pointer called head. And I want to have the length of the list. And this needs to be node underscore int. Okay. Now here's where I want to put my member functions. And like I said, you can't actually have member functions in a struct, but you can have these function pointers. And you can use them in a way that's very similar to the way you would use a member function. But they need to actually be defined outside of the struct itself. So let's see what functions I'm going to need in my linked list. I'm going to need one that will return the data, so my iterator function. So this is going to return a struct of node type int pointer, and we're going to call it iterate. And it's going to take as arguments the index that you're looking for and a pointer to the linked list itself. So in the class version or the C++ version, I didn't have to specify this. I could just refer to the items by their name within the class. But since this function actually exists outside of the struct, I'm going to have to pass a pointer to the linked list itself. So we'll say linked list of type int, and we'll call it linked list. And this is going to need to exist down here because the struct has to be defined before I reference it. And I need the okay. And one other thing I'm noticing right now is that my iterate function in the class, I made this private. And the reason I did this is I don't want users to directly iterate over the linked list. I want them to use other functions that themselves use iterate. And I can actually still do this in C, I just need to do it in a different way. And that's going to involve not defining this here. You'll see where that goes in a minute. So what I do need to define here are the functions that I actually want to use in the struct. So let's say I want my replace function or my insert. So insert returns void. We're going to call it insert. You're going to pass it int data and a pointer to the linked list itself. I also defined that wrong up here. I put the pointer in the wrong spot, but that's okay. Okay, and I'm just doing function prototypes here for now. This is the header file. That's kind of a benefit to C actually, because if you remember using the class templates in C++, I wasn't able to use function prototypes, and so the header file became a bit messy. Whereas here in C, I can't make a class template at all, so I have to manually do all these things, allowing me to use my function prototypes again. So some pros and cons there. Let's create the other prototypes though. So we're going to have one that is going to remove a item from the list. So void remove is going to take int index and struct linked list of type int linked list. And I made a mistake here. We are going to insert data, but we are also going to insert the index. We have to insert it at a particular place. And I believe these need different names. So first of all, I can't overload my functions in C. So I have to be more specific. If I add a linked list for floats, I'm going to want another insert function. And that function is going to have a different name from insert. Also, the function I'm going to create here, remove, has another name in C, so I can't use just the name remove, so I need to be a little more explicit with these names. So I'm going to call it insert node int, and we're going to say remove node int. And these are rather unfortunate names for functions, but this is where my object-oriented background is going to come in handy. I'm going to be able to actually rename these functions within the struct itself. So when the user is actually using them, they will not have to worry about these weird names. They'll just be able to reference whatever insert function is included within the struct. You'll see that in a moment. So last, we need one that will return the data. So int retrieve node int, let's call it retrieve data int, not dat. And it's going to take int index and a pointer to the linked list. So one thing that exists in C++ that does not exist in C that I actually do want is a constructor. I want a function to initialize some of the values in the linked list automatically. But I will have to do that again in a slightly different way. So I'm going to create a prototype function for that. So we'll call this struct linked list type int. And it's going to be called linked list int constructor. It'll take no arguments. Okay, so now let's go on to the actual C file. And let's clear some space out here. I want my C file over here, and let's do that. Okay, and here is where I get to actually specify what would be considered the access levels for some of these functions. So in my C file, I can define functions that don't exist in the header file. That way, when you include the header file, you actually don't get access to the ones that only exist in the C file. But the functions in the C file themselves are still compiled. So I can use them in the C file without allowing access outside of it directly. Before we can actually move on to the header file, though, I want to put my function pointers inside the linked list struct. And here's where I get to actually rename them. So I'm going to call a void function, and it's a pointer called insert. And here it would be insert node int, but here I can just call it insert. That way, if you refer to the insert function of the linked list node or the linked list int, this is the function you're going to get. And then I have to specify what you're going to pass to this. And we're going to pass it int index, int data, struct, linked list, int pointer, linked list. And we'll have another one for void remove node int. Actually, again, I'm making a mistake. We can just call it pointer remove int index struct linked list int pointer linked list. All right, and now we have the retrieve. So this one's going to return an int retrieve. And again, I keep forgetting to do this. We're going to actually define that as a pointer to a function that gets passed int index and struct linked list int linked list. So this allows me to actually rename these functions, which is really nice because in this file, I'm going to want insert node int, I'm going to want insert node float, insert node character, all of those things. And by including them as function pointers within the struct, I get to rename them to something a little more elegant. So the actual user experience of my linked list is a little bit cleaner than it would be otherwise. So let's move on from here. What I want to point out is that I don't want the user actually calling insert node int outside of this specific struct. So I actually don't even want to define these in the header function. I only want the user to have the ability to call a constructor or directly instantiate a linked list. So let's come back over here, and this is where we're going to put all of these. I need to make my correction here. And just like in my C++ file, I don't want the user to have to worry about creating and destroying nodes themselves. I want my linked list to do this for them. That way they can focus entirely on the data that they're actually worried about. So we're going to create a create node function and a destroy node function. So we'll call this struct node int pointer, going to be called create node int, takes no arguments, and then we'll have a void function called destroy node int, and it's going to take a pointer to the node. And we need to actually specify void in this function. Odd, that's not what C++ requires, but okay, they want something a little bit different. All right, so that should be all of our function prototypes. We are going to have a create node. Oh, we also will want to define the constructor over here, but I don't think we need a prototype for that since we have that in the actual header file. So let's define our constructor first. So we'll say struct linked list of type int, linked list int constructor. And what is this going to do? It's going to define a new linked list object and then instantiate some of the members and then send it back to the user. We're going to create a new linked list object. So int new list, and then we're going to say new list dot head equals null, new list dot length equals 0. And then we are going to actually define what our functions are going to be. And null doesn't work over here. Let me look up what I'm supposed to put in there again. Okay, so the problem was I had not included the standard library. That's all I needed to do. So let's move on. We are now going to define what these actual functions are referring to. So the insert function, new list dot insert equals the name of that function prototype. So insert node int. And we don't need any of these members. We're actually just going to use the name of the function. So we have a pointer in the struct, and what I'm doing here in the constructor is pointing that pointer to the actual function. So when we actually use this, I will be able to say something like new list dot insert, pass it the parameters, and it will run the function that I'm specifying here. And this sort of lets me change the name of the function so that a linked list of type int and a linked list of type float can both have an insert function, but they refer specifically to the functions that they are actually going to use. And to me, this is a very good thing. I wonder how people who actually use C often feel about this. I imagine I'll hear it in the comments, but anyway, this is how I'm going to do it. So we'll define the others, new list dot remove equals remove node int. And then new list dot retrieve equals retrieve data int. And I'm wondering if I should actually put this constructor itself inside the linked list struct. And I think I am going to try that. I don't know if it's actually going to work because I'm going to be returning the same type that it is and then setting it equal to itself. Let's find out. So struct linked list int constructor. Yeah, we'll call it constructor, and it takes no variables. So now we can say new list dot constructor equals linked list. There it is. Okay, so maybe we can do that. That's pretty interesting. We'll see how that actually works in the final result. I did some experiments with this before I actually started making this video, but I did not try this, so we were finding out together. And then the last thing it needs to do is actually return the new linked list that it just created. So we will return new list. And I would worry about something recursive happening here, where the new list that is returned contains this constructor, which itself creates a new linked list, which would contain the constructor, which would create a new linked list. So I don't think that's going to happen because I'm going to have to explicitly call the function before it actually runs or tries to do anything. So I don't think that's going to be a problem, but we will find out. Anyway, this is all good to go. This is our constructor. And so let's now create the other functions that are in here. Let's use the create node int first. So struct node int pointer create node int, passing it void. We don't need to say that here because this is the actual definition. And if you remember in my C++ version of this, I was able to just use the keyword new. And the keyword new is going to do a lot of things for you in C++. In C, however, you have to do those things manually. So this is going to look slightly different. In fact, this is the way I did it in C++ originally before finding out that using the keyword new would actually do all these things for me. So I'm glad I learned that because now I actually get to use it. We're going to create a new node pointer. So a struct node int pointer called new node. We're going to set it equal to a function called malloc, or memory allocation. And this is going to allocate memory on the heap for this object. So we're going to have to cast the result of malloc to a node int pointer. So we're going to say struct node int pointer malloc, and then we need to pass it the size of that struct. So struct node int. Now we can actually create a node int object and put its value into that memory address. So we're going to say new node. No, that's not what we want. We want to say struct node int. And I'm going to put a name in here that's a little more specific. We're going to call this its address. And we're going to call this one new node instance. Now, I want to say that the dereferenced new node address is equal to new node instance. And for simplicity, I actually, instead of making this void, I want them to actually pass in the data that they want to put in this node. So we'll say int data, and we are going to say new node instance dot data equals, we need to put it in here as well, equals data. And then let's also say new node, not address, instance dot next equals null. And then we need to return the actual pointer. So return new node address. So that's how we're going to create the new node. And this is a little more complicated to do than it was in C++, because in C++ I can just use that keyword new, and it's going to do all this stuff for me. But here I have to do it manually. And that is kind of back to the abstract discussion of the differences between the language is. That is the crux of the difference. In C++, there are a lot of nice features that do things for you, whereas in C, there are a lot of things that you have to do yourself. And I would kind of make the analogy to driving a stick shift versus a manual car. Perhaps it is true that driving a stick shift actually gives you better gas mileage or performance or something like that. I don't know if it's true. Stick shift drivers, don't yell at me for that. I know nothing about cars. So if that is true, that may be true here as well, that doing this manually and not having C++ decide all of the things that are going to happen when I try and do this may be more efficient. The difference is probably negligible. And really what I would say is that you have to do all of these things yourself in C. And that could be a positive or a negative. Why would you drive a stick shift when there are manual cars? Well, if you are a fan of driving, then driving a stick shift would be really appealing because it's a more into the process way of driving. You actually have to feel the car and actually control more aspects of the car. So those who actually like driving may want to drive a stick shift for that reason. And for someone like me who really likes programming and likes thinking about what is going on in the hardware when I write this software, this is really appealing to me. I don't want the language to do a lot of things for me. So this is appealing to me. If you, however, don't like having to worry about memory allocation on the heap versus the stack or where things are going to be moving and all of the minute little functions that are going to have to be run, this might not be what you want to do. As you can see, it's taking a lot of manual work for me to do something that is one line of code in C++. So that is so far what I have noticed to be the significant difference. That being said, I can still get the things I want out of C, and I actually like doing it this way. So let's move on. Okay, so we also want our destroy node int. So we're going to say void destroy node int, and we're going to pass it struct node int pointer node to destroy. And here we are just going to call the function free, and we're going to pass it node to destroy. Now this is a bit unnecessary since I'm having a function just call another function, and the only reason I'm doing this is to have slightly simpler naming conventions. I create node int and destroy node int. Those are obviously going together versus create node int and free. It's from the name itself, it's not obvious that those are trying to do two parts of the same thing, creating and destroying those nodes. It's the only reason I'm doing that. All right, so now we get to our iterate function. So this is going to return struct node int pointer called iterate. Well, it's not called iterate, the function is. We're going to pass it int index, a struct linked list int pointer called linked list. And this is our function where we are going to actually move through the linked list from the beginning to the end. And here is a good opportunity for me to prevent some errors. So the user may specify a negative integer for the index that they want, or they may specify one that is greater than the number of items in the list. And in order to prevent that, I'm going to use an error message. Now in C++, this is as easy as using the keyword throw, but C does not have errors built into it. I need to do it in a slightly different way. And so what I'm going to do is call printf, and in order to call that, I'm going to need to include stdio.h. We're going to printf index out of bounds, but that is a little premature because I need to use my if statement. So if index is less than 0 or index is greater than linked list length. And I think this should be greater than or equal to linked list. Yeah, because it's going to be 0-based indices. So if there are 5 items in the list, the highest number you can put in here should be 4. So greater than or equal to, we're going to print this. And let's go ahead and add that. Cut that, put it there. And then we're going to exit. And we're going to exit with a -1. Or let's exit with 9, because I think -1 is just going to loop back to 255. Okay. Otherwise, we are going to actually iterate through the list. And just to throw it out there, I experimented with this a few times, and simply by putting my error message in this iterate function, which is called by all of the other functions, I only need to have this one place to test for errors, and that makes my code a lot simpler. So now let's go into the actual meat of this iterate function. We're simply going to start at the head of the linked list and move through it until we reach the index that we want. So what we are going to do is create a cursor object. So we'll call it node int cursor. And this is going to be a pointer. And we need to say struct. And this cursor is going to be equal to linked list head. Okay. Now what we're going to do is a for loop. So for int I equals 0, I is less than index, and I plus plus. We are going to say cursor equals cursor next. And then we can simply return cursor. Great. So with our iterate function, we're going to be able to move through the list, and then we can use our insert and remove functions to actually operate on the list. So let's create those. I'm going to clear out this window because I don't need it anymore. So we'll say void insert, and insert is going to take index, data, and the list. So int index, int data, and int, not int, but struct linked list int, pointer linked list. And I think I was actually using the wrong names for these because we need to specify what these are. Do I need? Yes, I do. I do need to specify int for these. So insert int and iterate int. Is that what I called it? Insert node int and iterate int. Okay. Yeah, so you can see there how having to use a different function for every type of node that I will eventually create makes these names a little bit unpleasant to work with. And that's why I wanted to create my function pointers inside the struct. That way I can say, okay, the struct for this struct, insert refers to insert node int. And then when I'm outside of this file and this header file, when I'm actually in the main program trying to implement this linked list, I can simply say linked list.insert, and it will call the right function. So let's continue on. So insert is first going to get the cursor for the item before the index we want to insert. So what we're going to do is say struct node int as a pointer called cursor equals iterate, and we're going to pass it index -1 and linked list. And the reason we want the item before the index that we want to insert it in is because when we do the insertion, we have, let's say we have these 4 items, and I want to put something at index 2, which is the 3rd item in the chain. Depending on how my camera mirrors this image, it might look a little different from you, but this is the starting position. So 0, 1, 2, 3. As if I want to put something in position 2, what I need to do is say this new item has a next value pointing to this item, the old position 2, and then the thing in position 1 is going to have a next pointing to the new item. That is how we insert it in the middle there. So I have my cursor pointing at the item before, and now I need to create the new object. Actually, I think I want to do that before I get the cursor. No real reason, doesn't make a difference, but that's how I want to do it. So we're going to say struct node int pointer node to insert equals create. No, actually we want to call linked list. No. And not that either. We need to specifically call the create node int. And we're going to pass it the data. Okay, and then we will get our cursor. And it doesn't like, okay, it's fine. So we'll get our cursor, and then we can say that the node to insert's next equals the cursor's current next. So node to insert next equals cursor next. Then we can say that the cursor's next is now the node to insert. And there we go. We have successfully inserted something into the list. Now we want to remove something from the list. So void, what do we call this one? Remove node int. And this is going to take int index and struct linked list int pointer linked list. Great. Okay. So here we need to do something similar. Again, if we have these items in our list with 0, 1, 2, 3 as our indices, and we want to remove the thing in position 2, we need to get to the item before it and say that this thing's next is now what was this thing's next. Then we need to delete this item, and that's how we remove something from the list. So what we can say is first we want to get the item to, what do we want to get first? We want to get the cursor first because that's how we're going to actually get the item to remove. So we'll say struct node int, let's get that right, pointer called cursor equals iterate int, passing it the index -1 and linked list. Then we want to get the item to remove. So struct node int node to remove, and that's going to equal cursor next. Now we can set the cursors next to the node to removes next. So what did I do wrong here? Spelled it wrong. Okay, so the cursors next is going to equal node to removes next. And then we can simply remove the node. And what did I call that function? Remove node int. No, that's not what we call it. That's this function. That would be recursive. What did I call it? Destroy node int? Yes. And we're going to pass it node to remove. Okay, that's how we get the item to be removed from the list. And the last thing to do is actually retrieve the data out of the item. So we can call this void retrieve. And what did I call it up here? Retrieve data int. I'm really seeing how not being able to overload functions is quite inconvenient in C. I'm having to develop this whole workaround where I have exactly the same function, just specified a different type. I'm glad, though, that I can actually use these function pointers in the struct, and that's going to make it a lot easier for me to actually implement this linked list later. All I need to do is specify that I'm using the int once, and that's when I actually construct an instance of my linked list struct. By doing that, I'm going to have all of the correct functions, the header file stays pretty clean, and I get to use some easier names. So I'm pretty pleased with this so far. Anyway, we'll call it int index, and we want a struct linked list int pointer to linked list. And we are just going to call the iterate function. So struct node pointer cursor equals iterate int. We're going to go to index and call linked list. And then we're simply going to return, and this needs to be int. So we will return the cursor data. And what does it not like here? Does that solve it? Yes, okay. So this should be all I need. Let's open these files up side by side again so I can really show you how I am managing the access levels for the user. So when the user actually creates an instance of a linked list int, they're not going to be able to call create node int or destroy node int or iterate int directly. They are going to be limited because the only thing that the header file includes is this. Now, when they actually instantiate a linked list int, then it is going to call, well, they are going to call its constructor, which we have set in here. And the constructor is going to point all of these pointers at the functions I want them to use defined in the .c file. And that is how I'm giving them access to these functions I just created. I've been able to change their name, and I've created limited route in which they can actually get to those functions. They have to get to it through the linked list object itself. So this is a very object-oriented approach to the language C. It's not traditionally done this way as far as I know, but this is how I'm approaching it, and I think it results in some pretty clean code. And the only thing I am considering now is this constructor again. Remember, I said that in my experiments, I did not actually include the constructor as part of the linked list int. And I don't think I actually can. And the reason is if I have the constructor as part of the linked list int, then they are not going to be able to call it. So I need to call the constructor before I can define what these functions are actually pointing to. But if I only have the constructor as one of these pointers, there is nothing that is going to set that value. So actually the constructor should not be a member. And that is unfortunate. I would have liked for my structs to just have a pointer to a function called constructor, and well, maybe I still can. Yeah, I suppose I can. Well, no, I can't. I can't, because I have to use the function to actually define what the constructor is pointing to. I can't do it directly in the struct itself. So unfortunately, the linked list int constructor is here to stay. But give me a few minutes here. I'm going to create a test file just to show you how this works, and I will be right back. Before moving on to the actual test file, I want to address one other thing, and that is that I need to handle it carefully when the index the user is trying to change is the head of the list. So let's revisit these functions really quick. I'm going to put them in brackets, put them on new lines, and let's give it a tab. And we'll say if index is 0, we need to do this different. So we are going to say that the head is now the new object, and the new object next is the head. So we are going to either way call this. So we'll define that up there, and then we'll say node to insert next equals linked list head, and then linked list head equals node to insert. And down here for remove, we need to do something similar. Put those in brackets. And let's not forget our else. So if index equals 0, we are removing the head. So in order to do this, we need to point the head at the next object in the chain. So the head's next, and then delete the head. So we will say struct node int node to remove equals head, linked list head. Nope. Okay, then we can say linked list head is equal to node to remove next, and then we can destroy node to remove. There's some redundancy in this code, so I'm going to take this out here and here and just put it down here. Because no matter which path we take, we're going to destroy the node. Oh, but that's a scope problem. Of course it is. So, is there any other way I can do that? Yeah, I can. So instead, I'm going to take the cursor. I'm going to first get the cursor. And then I'm going to set, nope, that's not going to work. I'm just going to have to do it inside each one separately. So we tried. The problem was that node to remove has a scope that only exists within each part of this control structure. So in the if or the else independently. And if I try to iterate to get the first item in the list, it's going to basically give us -1 as the thing to iterate to, because it's going to want to get the cursor before the item we're trying to remove. And that will just cause an error. So I do have to do this separately here. So that's okay. And then let's not forget to keep that length counter up. So we'll say list, linked list, length minus equals 1, and linked list length plus equals 1. Okay. I'm going to go back to that test file, and I'll be right back. So here you can see the test file that I created, and let's walk through what happens. First, I create a new instance of my linked list int struct called list by calling the linked list int constructor. And that handles all of the instantiation of those pointer functions for me. Then I simply create a for loop that is going to insert the numbers 1 through 10 in each of their respective places into the list. And notice I have to pass the address of the list itself into that function. Also notice that here, when I want that function, while in my linkedlist.c file, it was insert node int, over here I can just say list.insert. And that's going to call exactly the function I want. Then I can call list.remove twice. So we're going to remove what's in index 3 and 7, which should be the numbers 3 and 7. And then we're going to insert the number 99 in position 1, again passing it the address of the list. And then I just iterate through the list through all 9 elements, because remember I took out 2 and added 1. And I'm going to print out what data is in that index. Then I will try to ask for an index that is out of bounds, and I should get an out of bounds error message, not in the way that C++ does, where they actually give you actual error messages, but in this C way, where I print a message saying there's an error, and then I just exit the program. Now, the last thing I want to show you before actually running this is what this actually looks like when the user is trying to use it. So if I want to call one of these functions, I can say list dot, and the only things I have access to are the actual values of head and length, and then this insert, remove, and retrieve functions. I don't have access to create node int, or destroy node int, or iterate int, or insert node int, or remove node int. None of these functions I have direct access to, because I only define them in the .c file. The only things I have access to are the ones defined in the .h file. So this allows me to create something similar to the access abilities of C++. So this is my object-oriented background coming in. So I'm going to delete this. I've already compiled it. And I'm just going to run it. And you'll see that it prints out each item of my list and then gives me my index out of bounds problem and then shuts down. So that is my C version of a linked list. And next, I'm going to actually try and work on the same web server in a similar fashion in the C language. So if you've enjoyed this video and you learned something, feel free to leave a like, subscribe to the channel, and all of that fancy stuff. And I will see you in the next episode. Toodaloo.